Okay, awesome. Can everybody hear me okay? Cool. All right, so with that, we're going to get started on our next session. This session is titled Materials Matter, Materials for Every Application. So I'm Evan. I work at Formlabs on our product marketing team. I'm going to speak to the materials side of the equation and our awesome material portfolio here at Formlabs. And then I'm going to hand it off to Ryan Laprise, who's a prototyping engineer at Microsoft, and he's going to speak to how these materials enable really awesome applications at Microsoft's prototyping lab. So with that, let's get started. Okay. Maybe. Oh, okay, there we go. Hopefully I didn't over-click that. Okay, I think we're good. So I'm going to open with this question that I'm trying to answer in my half of the talk, which is how do we organize our 60-plus materials here at Formlabs? We have a lot of materials. Materials are very complicated things. They have a lot of different properties. So how do we think about it? And I have a picture and a quote from a famous Swedish scientist here who was responsible for binomial nomenclature and knows a thing or two about naming things and the importance of naming things as a way to convey knowledge and understanding. So with that, I'll dive into it. So these are the way that I think about our materials, but it's not necessarily the only way to think about our materials. Materials are complicated, so you can organize them by application, by property, and a whole bunch of different things. But the way that I like to think about them is starting from what are some really versatile materials. So these materials have a really good blend of properties for a bunch of different applications. On the SLA side, we have our gray V5, our general purpose V5 family, all the way on the left side of the column. We just launched the 5th generation of those materials this year. They're really awesome and have better properties across the board. And within that family, you have gray, black, clear, and white. On the biocompatible side, we have sort of a similar analog to this in the general purpose Biomed family. And in that family, it's Biomed white, black, clear, and amber. Same thing, they have sort of properties that are balanced for a wide variety of applications, and with the added benefit of being biocompatible. You'll notice in the names of these materials, the name is based off of the color or the aesthetic of the material. These materials are going to give you the most aesthetic options of our portfolio. Going down the line on SLA, the next material is fast model resin. So like a general purpose material, but faster is basically the idea behind fast model, so if you need to print things quickly. And then if these materials didn't give you the aesthetic options that you wanted, you can always go to Color Kit, which lets you dye your resin to a custom color and have whatever color you want your resin to be. And then on the SLS side of the spectrum, our jack-of-all-trades material for SLS for a long time has been nylon 12. It's got really good properties and a little bit higher heat resistance than the SLA general purpose materials. But at least up until very recently, if you wanted to print an SLS, you were kind of locked into a gray material. But with the introduction of nylon 12 white, not only can you now print white SLS parts in nylon 12, you can also dye those parts to be whatever color you want them to be. So finally getting to sort of the aesthetic options that we've had for a really long time for the SLA side of the family. So the next category I'm going to talk about, the next grouping is tough materials. And so toughness is a really important property in material science, and people sometimes mistake it for strength. Strength is, how hard can you pull on something before failure, or how much stress can a part withstand? Toughness is actually measured in energy, not in terms of force or stress. And so it's the amount of energy absorbed before fracture. So whenever we're looking at a TDS for a material property and we're trying to evaluate toughness, we need to look for something that has units of energy. So the most common way we do that is with impact strength. That will have units of joules per meter, typically. But there are other ways to measure it as well, like worker fracture, which is done at a slower strain rate. The least tough material in our family is called Tough 2000. So it is the stiffest tough material. When we have materials that have a number in the name, usually the number is the tensile modulus for the material. Tensile modulus is how we evaluate stiffness in materials. So Tough 2000, having a 2000 next to its name, is stiffer than Tough 1500. At the same time, tough materials usually trade stiffness for increased toughness. So Tough 2000 is stiffer than Tough 1500, but Tough 1500 is tougher than Tough 2000. So that's kind of the way to think about the portfolio is you're going down in stiffness, but going up in toughness. And so at the end of the spectrum, you have durable and biomed durable, which are considerably less stiff, but they are tougher still, and kind of the tougher of sort of the standard resins in our portfolio. The SLS side has a really awesome material that we launched this year called Nylon 12 Tough. That is tougher than standard Nylon 12 and has really good properties as well. It falls about between 2,000 and 1,500 in terms of its toughness. And the next option for toughness in the SLS materials portfolio is Nylon 11. Nylon 11 is even tougher still, but it's a little bit harder to use because you're going to need nitrogen to ensure that you can get really consistent results and lower refresh rates. So that's the tough family of materials, which I, again, have grouped across SLS and SLA and biocompatible materials all in the fold. The next family we have is going the other direction. So these are our most rigid materials. In this case, we're going to have that elastic modulus number be higher. So rigid 4,000, rigid 10,000, you can see that number is going up. And these materials are most frequently filled with something. That's how we usually get stiffer plastics, is we add fillers to them to get stiffer parts. So starting with our least stiff material is Nylon 12 glass filled all the way on the right. Nylon 12 glass filled has a glass bead filler. Rigid 4000 is one of our first glass filled materials, and it's a glass filled SLA material. Nylon 11 carbon fiber is a long fiber carbon fiber reinforced material. And one thing to call out is usually these rigid materials sacrifice toughness for stiffness. So to get increased stiffness, usually you're sacrificing your elongation to break and your toughness. But in the case of Nylon 11 carbon fiber, the long fibers actually help with impact resistance. So whereas Nylon 12 glass filled, rigid 4000, and rigid 10,000 all decrease their impact strength for their improved stiffness, Nylon 11 carbon fibers actually got a really good impact resistance. But just like Nylon 11 without carbon fiber, it does require nitrogen to use, and it's a little bit more involved than some of the other SLS materials. Our most stiff material across the entire portfolio is a really big fan favorite. It's called rigid 10,000 or rigid 10K, and that is for its modulus, which is at 10,000 megapascals. So another group that I have is now going the other direction again. Some materials have a really low elastic modulus. In fact, their elastic modulus is so low that elastic modulus doesn't become a really useful criteria anymore, right? It takes so little force to elongate these materials that we kind of want a different metric to evaluate them and put them next to each other. So we use a property called hardness. Hardness is just localized deformation in response to stress. So we're still doing a stress to deformation relationship, but it's localized in the material. And we measure this with a shore hardness gauge is one common way that we do this. And you're just pressing into the material and measuring the response. So it's just basically an artificial scale. We're typically using the shore A hardness scale. And you'll see that all of our materials are labeled with their shore hardness value on the material. So our least soft material is TPU 90A, and that has a shore hardness of 90A. It's our only elastomer within the SLS family. Then we have the flexible ADA and BioMedFlex ADA, which are at the ADA durometer, so getting a little bit softer, but still in sort of the more harder end of the softness spectrum. Then going to some really soft materials, we have Elastic 50A and its biocompatible counterpart, Biomed Elastic 50A. These materials offer really good elongation and softness, and they're softer still. Silicon 40A is our softest material. It actually uses a different chemistry to achieve this softness, but it's the softest material that you can print here within Formlabs material portfolio. Moving on, there are some materials that don't really fit into this bounding box that I've laid out between elastics and rigid materials. And they also don't really fit into the typical material portfolio of Formlabs, where I grab a cartridge, I grab a tank, I put them into my printer, and I print my parts in a standard workflow, or in the case of SLS, I add powder to a hopper and go through and sift and blast it. There are a couple materials that don't really follow that workflow, but also don't really fall into this bounding box of properties. So we're bringing back an old brand name that we had for these types of materials back when we launched the original ceramic material that we had. And that is called Form X. And so the idea is that these materials are for experts. They exceed the capabilities of the existing printing portfolio, but they're not as plug and play as you would expect with a traditional Formlabs material. They require extra equipment that's not provided by Formlabs. They require more attention to detail in the workflow to get really good, consistent parts, with taking a lot of care in the post-processing steps to ensure that everything goes well. But at the same time, you're able to really get amazing properties out of these. So polyurethane and alumina 4N are kind of the two things that are in this portfolio to start. And if you look at polyurethane rigid 1000 resin, you'll see that it actually has a really similar tensile modulus to durable resin, which I talked about being a really tough SLA material. But it has a almost double the impact resistance. So at the same modulus, you're getting double the impact resistance. If you go ahead and drop the modulus to what it is for polyurethane rigid 650, you're able to get to like 3 to 4 times the toughness that you're getting in the standard SLA portfolio. Likewise, the fun anecdote I have for alumina 4N is if we named it like we did for the rigid materials and used the elastic modulus in the name of the material, it would not be called alumina 4N, it would be called rigid 390K or rigid 390,000 because that is its tensile modulus. It is just that much higher than a rigid 10,000. It's higher than a stainless steel. It's a very, very stiff material because it is a ceramic at the end of the day, not a polymer. Awesome. So that is Formex. Diving into another category of materials I have, these are specialty materials. So these are ones I'm not grouping by mechanical property because they rely on another property to be their defining characteristic. So rather than toughness or stiffness, these materials have a defining characteristic around flame retardant, for example, ESD, so flame retardant being defined by having a UL94 V0 rating, ESD being defined by its surface resistivity, and high temp being defined by its heat deflection temperature. On the SLS side, I've put polypropylene into this family. Polypropylene is not significantly tougher than nylon 12. It does have higher elongation at break, but its really defining characteristics that differentiate it from a nylon 12 are things like chemical resistance and moisture resistance, as well as its ability to act as an analog for injection molded materials like polypropylene, which are all kind of separate from its standard mechanical property profile. So jumping on to another category that we've had for a long time is castable materials. And we've had castable resins for jewelry applications. They come in the form of various waxes, and they can be burned out, and then you can pour metal into a mold to get a final metal part. This year we released clear cast resin, which is a resin that is for investment casting, but for investment casting larger parts at foundries for industrial and engineering applications. You're printing larger patterns, and you're using this tetrahedron lattice within the patterns to enable your parts to burn out cleanly, which is a really awesome material. There are some really great parts over at the expo if you guys want to check them out. Cool. A different way of naming our materials is one that we use for dental. So I talked about you can also name or categorize materials by application, and within the dental portfolio, that's what we do. Our material for surgical guides is called surgical guides. Our material for custom trays is called custom tray. Just to keep it easy, it's for the application. And that's how our dental portfolio is named. We have a whole bunch of different materials there that I won't go into in too much detail. Then jumping on, one really awesome thing that we've done this year is open material mode. So we make a lot of different materials here at Formlabs, but we're not going to be able to make a material for absolutely every single niche that exists. So the way that we're going to continue to grow and continue to enable people to print more things is to enable them to make their own materials for their particular applications. And open material mode is our way of doing that. I have two really awesome customer examples here. One is from Figure Engineering, and they are printing masks for, or masking jigs basically for electroplating. So in this case, this screw is going to be electroplated, but you don't want to electroplate the threads because you'll change the thickness, the offset, the tolerances, and then your threads won't thread together. So the material is specifically designed for that application and what they need for doing that masking. On the engineering side of things, Polymed has a really awesome material that is bioresorbable. So it is designed to be put into the human body and then dissolve and be absorbed, which is really cool. Not something that we've ever done here, definitely outside of our knowledge bounds and scope. So really cool to see customers taking our platform and taking it even further to do some really, really awesome things. And then one other thing I want to call out is, like I said, this is the way that I think about our materials portfolio. It's not necessarily the only way to think about our materials portfolio. And so one really awesome tool we have, if you go to formlabs.com/materials, is what we sometimes call the materials catalog. And it is all of our materials listed, but you can do things like organize them by a particular property. Here I have it organized by ultimate tensile strength. So it is a ranked list of materials going down to ultimate tensile strength. And then you have sliders and filters on the left-hand side, so you can pick for applications. You can add another property. So here I think I slid a notched IZOD slider up a bit, so I want strong materials, or materials ranked by strength, but I also want a floor of how much toughness I'm willing to accept. And it's a really cool way to just explore our portfolio and to find things for your applications more easily than trying to read through every single TDS individually. So I want to call that out, and I encourage you all to use it as a tool because it's really awesome. So that is all I have to say. So I'm going to hand it over to Ryan Laprise, who's the prototyping engineer over at Microsoft, to talk about some of the applications that he does with our materials.
Thank you. Hi, my name is Ryan Laprise. I work at Microsoft in the Advanced Prototyping Center, and we're basically an all-encompassing like model shop and prototyping lab on the Microsoft campus in Redmond, Washington, and we kind of help support all aspects of like product development for Microsoft, so any of the hardware that they do. The majority of the company is software, but we're in one of the few buildings that does focus on hardware, and we help through the entire spectrum of product development, from initial concept ideation with the designers who are designing what our new products look like, all the way up to helping the manufacturing side, helping solve manufacturing either errors or like problems that they're having, and that can be anything from like fabric for our type covers on our tablets. We've had issues with kind of solving how the fabric adheres to the product, down to like machining aluminum buckets for tablets and laptops and stuff. We have a team of CNC machinists who will actually iterate tool paths to kind of streamline the production cycle. And so my job is, I'm a prototype engineer. My role is kind of called architect, or like CAD architect. And I work, probably 80% of my job is working with the designers and doing initial product concepts and getting the designers like physical models to hold and feel and evaluate. And so, oops. And so we do a pretty broad range of different prototypes. The designers are working on like initial concepts, like I said, where you're exploring things like aspect ratio, device thickness, and once you're further along in like the design process, you can get into more involved prototypes that are like machined aluminum. We paint them to look like real anodized parts, and yeah, you get really into the details of like making a model look like a real product, so that way the designer can hold it and actually really evaluate how that product is going to feel in the real world. And so to handle those requests, we do, in the initial stages, we do polyjet, a lot of polyjet parts, where surface finish isn't really critical. And then on the other end, like I said, we do CNC machined models. And where Formlabs has come in is we always want to make things faster, and the faster we can evaluate things, the faster we can move in the product cycle. And so where Formlabs came in initially, we were printing these kind of like drop-in connectors And so to make machining the like really nice models faster, instead of machining a bunch of internal components to put real connectors in, or sometimes we don't even have the connectors, we'll do just a side pocket in the side of the device. That's super easy to machine for our machinists. And we'll print like dummy connectors and throw those in. These are in gray here, but we usually print them in black so we don't have to like paint or anything. And that's super useful for like the SurfLink connector, which is like our kind of power connector. We have stock components that we could use, but sometimes the external geometry of the part dictates that we can't use a stock part. And so instead of machining really tiny details to get the look of a real connector, we can just print one and just tape it into the side of the device. And we do that for like USB-A, USB-C, and even some speaker meshes. We have speaker mesh that's on a little cutout on the side of our tablets. And that was super useful in the beginning stages of like developing that. And then actually we also did some elastic prototypes for our earbuds. And we eventually moved on to like CNC molds and casting real silicone. But the initial stages of prototyping and getting like the fit in the ear, we did a lot of elastic prototypes for our earbuds. And then I don't have a picture here, but we do have like headsets. I worked a lot on our Xbox headset. We had some really nice Surface headsets. And for those, we did a lot of polyjet models initially. And if you know polyjet, it's very brittle, or more brittle than we'd like to have for our models. And so where that came in, where we used Formlabs for that, we used a lot of like Tough 1500, Tough 2000 for the actual headband. And that made it so that we could print like looks-like models of headsets that won't snap when you try to like put it on your head. Because I don't know if you put a bunch of headsets on a table that are just like printed models in the middle of a design studio for people to review, there's going to be at least one person's going to walk up to that table and try to put that headset on. And if it's all a polyjet model that's painted to look like a real thing, we have people coming back to us all the time to like glue models together because someone picked it up and tried to put it on their head. And so the Formlabs tough materials have been super handy for that kind of stuff, just making the products more usable and much more useful to evaluate the look and feel. And then we use a lot of rigid 10K in our model shop. A lot of it's for like sheet metal stamping. We do a lot of prototypes for like shield cans on our electronics, like on our circuit boards. I'm not super familiar with that realm, but this model's from one of my coworkers who's done a lot of experimentation with that. And we have on site, we have like water jets and laser cutters, laser etching machines. And so we're able to cut out sheet metal parts and stamp them using printed molds. And that's helped immensely because our biggest bottleneck is usually on the CNC side. And so if we can bypass CNC machining and get a product faster, it's super helpful for us. And then I don't have a lot of pictures of our like work stuff just for confidentiality reasons, but I do have some like we're able to work on like personal projects outside of work hours, and I use that one to work on my car and also to kind of learn new processes, which only helps use those processes in our model shop. And so this was a lock cylinder that I was trying to make for my car. And we were messing with injection molding. We just got like a little bench top, just like manual injection molder for doing like overmold stuff, injection molding like Xbox components and stuff like that. And so using the rigid 10K, I was able to kind of get a feel of like one, mold design, and two, just how the molder itself worked. And so I was able to make some lock cylinders with some like pretty complex like side pulls and stuff And you can see like some of the details are super fine, and so like pieces break off just because of how rigid the material is, but the parts being so small and so fast to reprint, you can kind of treat those as consumables. And you can do like risky stuff like having zero draft on a part if you're just kind of messing around and having fun with it. And then this was another like passion project that I had. This was a fender mirror for my car, and a lot of the ideation on it was using Formlabs parts, mostly for the clear part that you see. This part right here is actually a clear Formlabs part that I sanded and then clear coated to get it as optically clear as possible. And then I was able to print a like cap to create a silicone mold of this so I could cast the clear part in a stronger clear material, just because the clear itself isn't, I didn't trust it to be on the road for thousands of miles. And so it was super useful just being able to print a cap that has all the indexing features and all the mold making features that I want. And I was able to do a two-part mold for that, and that's where that part came in. As well as this knurled part here is actually just a raw rigid 10K print that I painted silver. And then the lower stalks are printed in stainless using a Mark Forge printer that we have on site as well. And that picture at the end, you can see that was after a 3,000-mile road trip that I did with my dad in Utah. Drove down to Utah and back to Seattle, and everything held up like great. And so, yeah, we just kind of mess around, have fun, fail fast is a big thing at Microsoft, and yeah, just kind of utilizing Formlabs to get better looking products and better looking models for our designers, and getting it faster. And I think that's it, yeah.
Awesome. Cool. Just want to let everyone know that it's now a 30-minute coffee break. So if you don't feel like sitting and you want to get up and get coffee, please go and do that. Otherwise, we'll see you back here for the next session, which is what's new and latest applications about SLS.